Okay, so hello everyone. Welcome to NPTL Week 5 of Introduction to Robotics course. I'm your TS Suraj Borate from IIT Gandhinagar, PMRF PhD student. And as always, we will be discussing Week 5 assignment from one of the previous year, and hopefully that will help you solve your current assignments. Okay, so let's start. Okay, so pick out the correct ones from the following statement made about the actuating systems such as pneumatic, hydraulic, electrical systems where the three are contenders. Okay, so we have to find out which statements are correct. And the hydraulic actuators are the smallest in size for a given power rating. Uh, that answer is right actually. So why so usually what happens is for a given power rating, like if you see hydraulic actuators and the equipments that use hydraulics are pretty large, but then the power rating associated with it is also very large. Okay, but if you keep the power rating constant, then for that particular power rating, hydraulic actuators are quite small. One of the good example is Atlas robot. Okay, so Atlas is a humanoid robot by Boston Dynamics. Okay, now Boston Dynamics humanoid robot. So this humanoid robot you might have seen does backflips and parkour and all that stuff. If you haven't seen, please go and see. That is the best humanoid robot, most agile humanoid robot available, and it is able to generate such high torques. So it is actually a human-sized robot. Weight is also like quite comparable to a human. So it is able to do this backflips and all, which is like a normal human can also not do. Okay, so to generate such high torques and all, they used hydraulic actuators only, and they had to design this custom hydraulic actuators for the each joint and all. So I don't know how many of the joints are hydraulic, but they are using hydraulic joints with custom actuators. Okay, the second statement is that the size of actuators are nearly the same for a given power rating. No, that is not right. Different type of actuator will be having different sizes. Uh, and See, hydraulic and pneumatic system also require reservoir and all that stuff. Okay, pipes and all. So it is more clumsy and more maintenance is also required, and the size is also bigger. Okay, compared to motors. Okay, but the power that it generates for its size is very high. So that is why there, for a given power rating, the hydraulic actuators are small. So it is like, if the word given power rating is not there, then definitely we will not call hydraulic actuator small, because you might have seen motors which are so small, like coreless DC motor and mini drones and all. They are very small. Okay, so sizes of actuators are not same. Okay, then the third point is electric actuators are easier to control as compared to other variants. Okay, so electric actuators are easy to control as compared to other variants means uh, it is true, right? Why it is true? Because it is directly you can give electric current, and the current is very clean to handle. You can have a battery, and you can have ICs and all that stuff that can control the actuators. Whereas if you see hydraulic, you will have required piston, cylinder, bearings, valves, and all that stuff. So it is not so easy. Okay, and even from control point of view, the electric signal you can control, and you can program that signal, because even the ICs that are being programmed, the output is an electric signal. Whereas in hydraulics there is a fluid, or in pneumatics there is air. Okay, so you need to have lot of transformation of energies in between. So electric actuators are the most easy to control. Okay, so why my pen is. So last is a hydraulic actuators are maintenance free. That is totally false because there is a lot of leakage and all that stuff and oil and all that. So it's not easy to maintain that. Okay, a power electronic converter is used as an intermediate between power source and actuating motor because. Okay, so the converter helps to improve, no? So the role of the converter is what? Can anyone answer this?
Mechanical to electrical
No.
conversion.
So a power, they have called it electronic converter, right? So it is just like, see, what happens is there is a motor. Okay, so this is a DC motor. Okay, it might work on 12 volt, 24 volt or whatever it's there will be some power rating. Okay, then there will be some IC, integrated circuit. Okay, that will have the logic, let's say PID control or some reason we are controlling this thing. There will be some desired motion that has to be performed. So where that desired motion, that motion commands will come. That motion command will come from some computer, a Raspberry Pi, Arduino or something like that. Okay, and that command will be like, okay, I want this particular RPM or something like that. So that will be information, and as you know, information is communicated at 5 volt or 3.3 volt, right? So ICs perform at 5 volt. Now this 5 volt signal, you have to, but that 5 volt signal cannot drive this motor, right? This motor has to be driven by 12 volt or 24 volt. Now how do we achieve this? Okay, so there is some battery, obviously. There is this battery that will be giving power to both this IC and the motor. Okay, now this battery will be at, let's say, 48 volt or 12 volt or whatever. Okay, but it can provide the current that this motor requires. So what will happen is this battery will say, okay, I am giving you 2 ampere or whatever current or whatever voltage that is required to you, I am giving you. Okay, but this IC says that, okay, no, you should rotate at 12 rpm. Okay, now this conversion, okay, of, but this message is at what? 5 volt. Okay, so the conversion of this 12 rpm to a particular voltage, okay, that is done using the power converters. Okay, power electronic circuit. Okay, so this side there is information. Okay, that is a low power information. Okay, and here there is this high power components, motor and battery and all, and there someone should translate this 12 rpm, 250 rpm, 1000 rpm in terms of voltages, and these voltages are high voltages. Okay, and this information, irrespective of whether it is 1000 rpm and whatever, it is at a low voltage, 5 volt and all. Okay, so that is why you need some power electronics. So typically what we call this particular thing is, okay, if you see a simple application, we'll call it as motor drivers. You might have heard this term. So you have the, for DC motor you have this very famous motor drivers, L293D, L298N, like that. You will get this chip for 100 rupees and all, and you can control a DC motor. So what actually happens is there are two sides of this driver. Okay, and what you do is, on one side, okay, you connect the motor terminals. Okay, then you connect the power source. Okay, power source, and you connect the microcontroller. Okay, so the microcontroller will put a value from 0 to 255 on the these pins. Once 0 to 55 value is put, if the value is 255, it will tell, the circuit will allow entire power, whatever the power is there, coming to the motor. Okay, so this is high power side, this is low power side. So the entire power will travel to the this thing. When it will be saying 125, half of the power will go. Okay, so like that you can, map the rpm to some digital value, sorry, so to some analog value between 0 to 255, some value, It's actually not analog, discrete value 0 to 255, and then it gets uh, then it allows that much current to pass here. So that is a basic example of a power electronic converter. Okay, that is the simplest way. If you search on Google like how to control a DC motor using L293D IC and Arduino, you will get a code. It's a hardly 5 line code. Okay, and you can just buy this DC motor. Let's say like to 30 rupees you will get one DC motor, and IC you will get at 100 rupees. Arduino you will get 300 400 rupees. You can have it 500 rupees. You can test this out. Okay, so this is what a power electronic components are required for. Okay, to convert the control signals to actual voltages, because both the levels of voltages are different. One is operating at a digital logic level like 5 volt and all, and another is like the actual uh, high power level 12 volt, 24 volt, 48 volt, and whatever. Okay, so that is the answer. Second is the power converter helps to allow control and regulator power flow. Okay, third question, consider the following statement S and a reason R. So there is a statement and then associated reason, and we have to tell whether they are true or not. So if an AC motor is used as actuator, the power source to the drive should necessarily be an AC source. Okay, so there are two parts. AC motor is used as an actuator. So what is an AC motor? So AC motor will be having phases, right? So there will be so in DC motor you had only two terminals, and only one, like one will be positive, one will be negative, like that. Okay, but in AC terminal there will be more than one coil, right? And the the coils will be having current which is varying at some phase angles, or the coils are kept at some phase angles. So that will be covered in coming lectures. We will not go into detail of AC motors right now, but yeah, so you get some idea that AC motor uh, is there, and the power source to drive should be an AC source or not. Okay, so can you drive a AC motor using DC power source? That is the thing. Okay, so obviously the answer is you can or not. That is the answer. But yes, you can drive an AC motor with a DC power source. The best example is the quad rotors. Okay, quad rotors have brushless DC motors, which are essentially a type of AC motor only. So, okay, you cannot give directly an DC current to a motor. Okay, so there is something called as electronic speed controllers in between the BLDC motor and the power supply. That is the DC power supply of the drone. That is lithium polymer battery, LiPo battery. Okay, and in between there will be some electronic speed controller. So we'll just draw the circuit diagram for basic circuit diagram for the drone. Okay, so you have this LiPo battery. Okay, so LiPo battery has high current density, and compared to like, so it is like give higher current at a lower weight of the battery also. Okay, you cannot put a lead acid battery on the drone, it will not fly, it's very heavy. So LiPo batteries are lighter for what they provide. Okay, and this LiPo battery is connected to something called as electronic speed controllers, ESC. This ESC is also connected to a flight controller. Okay, the flight controller will give certain commands, and the power will come from the LiPo battery, high current, and then the output will be three terminals. Okay, not two terminals like DC motor. In DC motor, you for a motor only two terminals were there. Now there will be three terminals will be coming that will be joined with the motor, BLDC motor, which will also have three wires coming out. Okay, so there will be like three wires and three phases will be there. Okay, we'll go into details when that topic comes. But as you see, the power source is this is the power source. Okay, so this is a DC power source. All right, so that statement is wrong. First statement is wrong, but I don't know how a wrong statement can have a true reason. So, but let's see, read the, nevertheless, we'll see, read the reason. So, it is difficult to develop a power electronic converter that can convert DC power suitable to an AC power. So, they are say it's difficult to develop. So we are not being taught how to develop these controllers in this course. So, it can be difficult for us. Okay, but for electrical guys, they have sorted this out, and in industry there are lot of power converters available for this particular purpose. So it is for them it is not difficult, and so this is also false. So S and R are both false statements. Okay, so I think the answer would be third one. Okay, so let's move on to the next one. Okay, so a robotic application driven by an electric actuator is observed to have a periodic ripple of high frequency in the torque waveform. Okay, this ripple is likely due to what? Okay, so the answer to this, first of all, you should understand that torque, ideally we don't want any ripple, right? So we want some torque like if this is the torque curve, then we want the torque to be very smooth like that. We do, sorry, straight line, assume it is a horizontal line. uh, so we want this to be like this, but in practice you will get something like that. Some ripple will be there. Okay, ripple means oscillations, and what is the reason for this ripple is asked. So this is this high frequency ripple, they have asked for high frequency, why the high frequency ripple is there. Okay, so the answer to this is the switched operation of the power electronic converter, because the high frequency stuff is can be done only by electronics. Okay, the mechanical systems are low frequency systems. Okay, their natural frequency is not very high. Okay, so the shaft resulting in ripple, this all reasons are this is a mechanical reason. Long conducting wire drawn, this has nothing to do with that. Okay, yeah, because of this some noise might enter. Okay, but that is not the reason for a high frequency ripple. Presence of a geared interconnection, again this is a mechanical reason, and let's say there is some chattering of teeth because of that gear or something like that, for poorly designed gears and all, but that won't result in high frequency noise, that will result in low frequency noise. Okay, so the answer is the fourth, sorry, a answer. Okay, so let's move on to the next question. The impact of torque ripple on an actuator system, actuating system. So what is an actuating system? Actuating system means what? It is like whatever is the cause of motion in the robot is called the actuator. Okay, so let's say a robotic joint. Now joint, only motor is not the part of joint. Joint is made up of motor, gears, bearing, right? All that stuff is there. So let's say belt or whatever is the transforming, what say, power transmission part, that might also come. Okay, the motor, the encoders, the sensors on the joint. So the entire thing is called a joint. Now that particular actuator, sorry, the entire thing is called the actuator. Now that particular actuator, okay, is affect its performance is affected by what? Okay, let's say that actuator is supposed to perform at a certain torque. or desired torque. Okay, but what is going to affect the desired torque? Is it the first option is lesser of it if the impact is less of the torque ripple, the impact of torque ripple is lesser if its amplitude is more and frequency is less, right? So what does the, see, let's draw the graph. So if you have any doubt, stop me, okay? I hope the meeting is going on. Yeah. So if you have something like this high amplitude, so this is the this thing. Now this particular is the desired torque, and there will be some acceptable range, right, which is around this region. Now if the amplitude is high, definitely it is going to affect, right, because it will be outside the bound of the acceptable region. If you want the torque to be 2 newton, then you have some plus or minus zero point 0.1 newton, 2.1 or 1.99, but if due to high amplitude it will cross, it will go, let's say, 3 newton, that is not acceptable at all, or 1 newton, that is not acceptable. So this is not the answer. So the impact of torque ripple will be high if the amplitude is more. If amplitude is less and frequency is more, true, okay, uh, it is irrespective of frequency, high irrespective of frequency or high irrespective of amplitude. See, both frequency and amplitude will affect, okay, but uh, so the third and fourth options are not there, okay, so both are going to affect, but amplitude, if it is more, it is going to affect, and frequency, if it is less, it is going to affect. Why? Because mechanical systems are have their natural frequency. So what does the word natural frequency mean? Every object, okay, has some natural frequency, okay, it will vibrate at some natural frequency. If you match that natural frequency, then something called as resonance occurs. So what does happen at the time of resonance? That the amplitude of the oscillations will keep on rising, and that can affect the health of that system, okay, it can damage the system. So and the resonance for mechanical systems appear at a lower frequency. So we don't want the frequency to be low, and the impact of torque ripple, that is a negative impact, will happen when the frequency is less, okay. And so the question is that less impact will be lesser when amplitude is less and frequency is more, because when at higher frequency resonance won't occur for mechanical systems, okay. So 5b. So if you have any doubt, ask.
I had a doubt, sir. If
Yes.
if the amplitude is less, so won't it mean that the signal wavelength or the torque ripple wavelength is resonant to the actuating system?
No, no, the wavelength depends only on the frequency. See, amplitude means you can have a high frequency but low amplitude, like that, right?
Okay. Yeah,
Now,
yes.
what you are saying is low amplitude and low frequency.
Yes.
This is going to affect because the frequency is low. See, if frequency is more, it is not going to affect. Okay, so the amplitude is not causing problem over here. Amplitude can be low. That is only we want, because if high amplitude, then it will go beyond the bounds. Okay,
Okay. Okay.
yeah. So next question will go. It is on similar lines. Okay, so the following statement S1 and S2 made about the geared interconnection in an electrical based robotic arm. A gear is needed in actuator mechanism because the speed of rotation of the motor is much higher than the speed of movement of the arm. Okay, and gear helps to improve the mechanical reliability and efficiency of the actuator system. Okay, so there are two things given. The first one says that okay, there is the speed difference that is required. So the motor available is at higher RPM, and the arm should not rotate at that particular RPM. Arm should rotate at a lower RPM. Then we need to create some speed difference, because we cannot directly mount the arm directly onto motor, because if you mount, then the arm will also rotate at high speed, because motor is rotating at high speed. So how do we create this difference? So as you know, so for those who are from mechanical engineering, they might be knowing. For others, you can pay attention. So what happens? So assume this is a circle. Okay, so this is one gear, and this is another gear. One gear has smaller number of teeth. Okay, and it is around this diameter. Okay, circumference, and then other gear has a large number of teeth and along this circumference. So in one rotation of this gear will not complete its rotation. It will rotate lesser number. Sorry, like if you rotate this gear once, okay, what will happen? This particular point will come back here. Okay, but let's say this point only will reach here, right? Because this entire distance will be in this much area only, right? Because this is much bigger circumference, right? So this, for this one rotation, this might rotate only 0.25 rotation, right? So if whatever the speed of motor, if you connect motor to this gear, and if you connect the robotic arm to this gear, okay, what will happen? If the motor rotates one time, this particular arm this particular arm will rotate only one fourth of rotation. So you will get a speed reduction, because when this rotates 10 times, this is rotating only 2.5 times, right? So this is the reason why gears are used. Okay, to reduce the speed. See, even while you are driving the bike, the engine can rotate at only one speed. You cannot control the speed of the engine. Okay, now that accelerator and all, I'm not going into that stuff, but let's assume that the engine is at rotating at some speed. Okay, and you change the gear. What you are basically doing is, the engine is rotating at the same speed, but the output from the engine, okay, you are manipulating that. Okay, by saying that okay, I don't want this size gear, I want this size gear, so I will get a different speed. So I change this. Okay, instead of this gear meshing with this will mesh with some other gear of different number of teeth of different diameter, so that this ratio, that 1 is to 0.25, will be different now. Okay, so gears are required for change of speed, and at the same time they are required for change of torque also. Okay, so the first statement is true. The second statement, gears help improve the mechanical reliability and efficiency, that is false. Okay, in fact gear boxes are the ones that fail. Okay, because what happens is, it is subjected to lot of wear and tear. Okay, because it is constantly, the teeth are colliding with each other, and there is a lot of friction and wear and tear. So it can be cause of failure, so it is not a very reliable component. Also, because of friction, there is loss of power. Okay, lot of heat is generated and power is lost. So the reason, second statement definitely not the reason, first statement is true. Okay, so S1 is true and S2 is false. Okay, the terminals for making the interconnection to the power source or power converter, as the case may be. In the case of permanent magnet DC motor, get connected to the winding placed on the, okay, see, permanent, there are two type of DC motors. One is permanent magnet DC motor, and another is the wounded rotor motor or something like that. So what happens in wounded this thing, the important point you have to remember is the stator. In permanent magnet DC motor, the stator is by the physical magnets. Okay, the neodymium magnet or whatever, it is like a magnet. It's like a stone. Okay, so it is not created by use of electric current. Okay, whereas in the wounded type, the this magnet is create, even the magnet on the stator, see, on the rotor definitely there is a winding, but there are other magnets which create this field, right? B, this field is created. That field B is created using the winding in that, in the wounded type motor, wounded stator motor. So what happens is, in wounded stator motor, the field is generated so that you can further control the speed of the motor. Okay, so you get more flexibility in the control of the speed and torque. So but in case of PMDC motor, the whatever the connection are going to be taking place between the power source or the power electronics part is directly to the rotor windings only. Okay, because on stator there is no winding, right? So uh, the answer to this is the rotor. Okay, so stator is a permanent magnet, a stone, no electric current passing through that. A terminal on the stator and on the rotor, no, it doesn't make sense, right? That is, two are independently moving parts. Sorry, the rotor is moving, but it is those two parts are not connected to each other physically. Okay, both the stator and rotor, no, no. So the answer is rotor. Okay, so I think there should not be any doubt in that. So I will draw the diagram for you. So there are two magnets like this which generate some field. Okay, and then you will have some conductor that is rotating in between. This is called rotor. Okay, so there is no electric current passing through these two magnets, right? Only through rotor. So this two has to be given, this coil has to be given the power. Okay, now the remaining questions are numerical questions. Okay, so you had some doubts regarding this. We will try to pick that up along the way. Okay, so this particular question, so you should, in the numerical questions, you should know the formulas, uh, and uh, in the lecture also they have gone through the derivation of the formula. I will not go through the derivation now, but we'll apply the formula and see what is the answer. Okay, so F is equal to BIL sin theta is the formula. We will just have to plug and get the answer. So a long conductor of length 2 meter. So L is equal to 2 meter. 2 meter. Resistance is equal to zero point 0.5 ohm. Magnetic flux density B is equal to zero point 0.8. Conductor axis makes an angle. So beta is 30 degree. So sin beta will be half. Okay, determine the current. Okay, and the force given is 1 Newton. Okay, so if you plug all the values, then you will get something like I is equal to uh, F upon BL sin beta, right? And it will be 1 upon, let's say, what is B, 0.8 into L is 2 into sin beta is half. So this gets cancelled, 1 upon 0.8. So that will be how much? Let's say 0.4 into 2, right?
Sir, 1.2.
1.25, right? So this is the answer. Okay, good. uh, so this is a very simple question. right? Uh, Basically, what this is saying is there is some force that is generated on this coil, and that force is generated when the current flows through a coil placed in a magnetic field. Okay, and that is governed by a cross product, right? So it is like there is cross product between the current and the magnetic field. Okay, that is why that sine theta is the angle between the uh, current and the magnetic field is coming. Okay, so if both are in same direction, then there will be no force. When the current is perpendicular to the magnetic field, there will be maximum force, right? So that is the logic. Let's say, let's move on. Okay, so a rectangular coil of length 10 centimeter and width 8 centimeter and 40 turns is placed in a uniform magnetic field of flux density 1 Tesla. Now the coil sides are always perpendicular to direction of field. So beta is 90 degrees, so sine beta is 1. So that is why the formula which you see beside this thing doesn't have a sine beta in it, because sine beta is 1. By energizing with a suitable supply, the coil is driven against a constant mechanical opposition of 0.8 Newton meter. Okay, so there is some load torque which is 0.8 Newton meter constant. Now determine the current flowing through the coil in this case. Assume the coil resistance as 0.5. Okay, so again let's see what values we have. Okay, so we have been given length as 10 centimeters, so 10 into 10 to the power minus 2 meters. Then width is given as 8 centimeters, so what is the width? 8 into 10 to the power minus 2 centimeters. So if width is 8, so the radius will be 4 into 10 to the power minus 2 meter, and there are n is equal to 40 turns. Okay, flux density is 1T. Coil sides are always perpendicular, so beta is 90. The coil is driven against a constant torque of 0.8. Okay, so determine the current. Okay, so let's try to do this. So I will be what? T upon N B L omega, N B L W. Okay, so can anyone tell me how much it will come? Just plug and play. So T is what? 0.8, N is what? 40 into 1 into L is what? 10 into 10 to the power minus 2 into W is 8 into 10 to the power minus 2. So L into B is nothing but the area. Okay, area of the coil. L into W means. Okay, so what is the answer? Okay, let's try. This 8
So
will
it's 0.25. 0.25 is that.
0.25, is it? Or I think it is 2.5. Okay, so let see, this is the formula. The answer comes out to be 2.5. You can check your calculation. Okay, so if you feel otherwise, you let me know. So basically, let's do it. Okay, so 0.8. This is 10 to the power minus 4. It will go up. It will be 10 to the power 4 into 0.8. ठीक है, नीचे क्या है? 40 into 10 into 8. Let's say this is zero point 0.1, so this will become 10 to the power 3, 8 will get cancelled. This 10 and one more will go, so 100 upon 40. So 100 upon 40, so this is 2.5. Okay, so 2.5 ampere is the answer. Fine, no doubts.
Yes, I accidentally wrote 10 by 40. So
Yeah,
that's why I
yeah,
was getting.
yeah, yeah. It can only these questions you can lose marks only if you write a wrong formula or there is calculation mistake. Okay.
Yeah, I
Yeah,
missed out that 10 into 10 to the power minus 2. I accidentally took the centimeter value.
yeah. Yeah, the units are very important. You should always convert everything to SI unit. Okay. So that is a small trick that that is like can cut marks. Okay, even though you know everything, it can go bad. Yeah. It's very painful when you get wrong because of not converting. Okay,
Right.
so determine the speed at which the coil would rotate if the voltage supplied by the source to the coil is 10 volt. Okay, and okay, so now what they are saying is you have to find the speed at which the coil will rotate. Okay, if the voltage supplied by the coil is 10 volt. Now let's see, we got what we got last time. We got the current to be 2.5. Okay, so and we have been told that the resistance is zero point 0.5. So what we can do is we can see, apply this KVL formula. What is the KVL formula say? Okay, so which one of this is 10 volt? E is 10 or V is 10? This is 10 or this is 10?
So I think V would be.
So what is the difference between E and V?
E, I think, is electromotive force and V is this input voltage.
If the voltage supplied by the source to the coil is 10 volt. Okay, and what is electromotive force means?
It's actually that formula earlier, F is equal to BIL and sin theta.
So basically,
Yes,
na, to write this formula, I have written it directly. Ideally, what you should do is it should be like input is equal to output. Okay. So this is actually Kirchhoff voltage law, where KVL is there. We used to call,
right.
right? So what we do is we say that, okay, lot of, okay, huh. So we give V voltage. Now where this voltage is used, it is used, okay, to have some amount of voltage across the motor, okay, plus some amount of voltage across the resistor. Okay, so this was the input 10 volt and it was divided like this. Okay, and then if you do this, so you gave 10 volt over here, E plus IR. Okay, I we know is 2.5 and R is 0.5. So E you will get as, okay, so what will be the value of E? E will be 8.25. 8.25 volt. Okay,
Sir, 8.75. I think it will be 8.75. Ne?
okay,
2.5 into zero point 0.5.
okay.
10
What
minus.
10 minus 2.5 into zero point 0.5. So what is
It
2.5
will
into 0.5? It will be
8.75.
8.75. Okay, okay. So this is, see, I also did some calculation mistake.
Yes.
Okay. So, right, thank you. So,
Oh,
E is 8.75. Now, what do we need to find? We need to find the speed. Okay, so what is the formula that relates the speed and the variables which we have? What formula we should use?
No idea, sir. Need a bit help on this.
Hmm? So there is this formula. Okay, let me make some space to write. Yeah. So this is the formula. This formula gives you. Okay, so I will just box all the formulas that are important. Okay. This one. So this looks like omega, but this is W. We'll just, well, this is area. You think of this as area of the coil. You might have remember from your 12th standard. This was something like, BIA. Used to remember. Okay. So this is area. Okay. So this is one formula. So let's say at the end of the class we will make a list of the formula. Don't worry about it now. Okay, we will do some quick revision kind of stuff. Okay. So if you plug into this, you will get the value of speed because we have everything else. Now this R says that what is the radius of the coil. Okay, so radius of the coil will be half of the width of the coil, because if this is the coil that is rotating, okay, this is the width, this is the length. Okay, so this is like the two terminals coming out, so the radius will be this force, this part. Okay, because the force will be acting perpendicular to the current that is flowing. So if the current is flowing like this, the force will be acting like this. Okay, and the force into radius is the torque. Okay, so this is that radius. So this is the important trick in this question. The radius will be half of the width by this logic. Okay, so now if you substitute, so we got 8.75 is equal to 2 into 40 into B is 1, right? L was how much? L was 10 into 10 to the power minus 2, and R was 4 into 10 to the power minus 2, right, into omega. So now you just have to find the value of omega. Okay, so what will be the value of omega? So you have to do something like 8.75 divided by all this stuff over here. Okay, so I would recommend you to use calci, and the answer actually turns out to be 27.344 radian per second. Okay, now this unit you can get by you know putting all these units and seeing what it comes to out. If you have doubt regarding that, we can go into the units, but yeah, this you should be asked to give the answer at like 1 decimal accuracy, so that we have already got, and pay attention to the units. Okay, so here the units because this is, you just have to fill in the number, you are not going to write the units. But if it is a, let's say, a multiple choice question and they have given option where units are different in every option, then you may have to pay attention to that. Okay, so operation beyond the, okay, so 11th question we haven't done. Okay, so a PMDC motor has an armature resistance of 0.5 ohm. You are able to hear me, right?
Yes, sir.
Yeah, yeah. You can ask me if you have any doubt. A PMDC motor has an armature resistance of 0.5 ohm. The scaling factor K between the speed and EMF is 1.9 volt per radian per second. So the K value, so K, you know, it comes in this torque equation, right? So tau T is equal to K into I. So that K they are talking about. That is, that K value is 1.9. Okay. If the motor is energized with a supply voltage, so V is 240 volt, and constant load of 2 Newton, so torque is 2 Newton meter. Okay, so they use the word load, but it means torque. Okay, it does not mean force. Okay, but sometimes it can mean force also. So you look at the units. If it is Newton meter, it means it is torque. In earlier question they said force and they gave Newton. Okay, but it might be possible that they may say load and they give in Newton. So if they give in Newton, you take it as F. Okay, determine the speed of, you have to find the omega. Okay, for this particular question you have to use the this formula. Okay, this is the equation that we see in the lecture where sir shows the motor curves. Okay, what is the graph of the torque versus RPM graph? Okay, that those graphs na, voltage versus torque, and so we studied how the motor behaves, right? So that particular lecture you will see the derivation of this equation. Okay, you can use this equation because it relates the, see, the because in question we have given the scaling factor K, so we, from that we get the hint that we have to use this equation. Okay, and the question also has voltage and torque, and for to find the effect of voltage, right, on how, on the relation of torque and RPM, we use this, we derived this. So as you remember, we had something like this. Okay, so this is a equation of line, right? So this is a variable and this is a variable for the constant voltage applied. If we apply a constant voltage, then these two are variables. So what is the, what this is what, y equal to mx plus c kind of equation, right? Where m is what, slope is ra by k square, and the y intercept c is v by k, right? So this is like mx, right, plus c is equal to y, that kind of thing, equation, correct? So this will be something like this, a straight line where this y intercept will be v by k, right, and this will be ra by k square, slope, the slope. Okay, why the line is like this and not like this? The line is like this because the slope is negative, because of this minus sign. Okay, so this is the pictorial representation of this equation. So let's go back to the question. So let's just plug in the values. Omega is equal to 240 by k 1.9 minus Ra. What is Ra?
So
Point
here
five.
we'll take 0.5.
Oh, I
Sir,
got.
0.5.
Uh, okay, 0.5 and into T is equal to because I can't see anyone and suddenly sound came, so I got scared. Okay, t is equal to 1. So k is 1.9 square. Okay. Okay. So if you calculate this, you will get some RPM. So let me look at my notes and see what is the value. Okay, so if you calculate this, you will get 1203.574 RPM. Okay, now the important thing to note over here is, okay, when you get the value, right, you should always look at the question very carefully. Okay, here actually these are very simple chapter. Okay, but there is lot of scope for mistake, because here they have said in RPM. Okay, now the value that you will get is not in RPM. This is not this much. Okay, this will be something like okay, let's try to calculate this. Okay, can someone put this value in calculator? 240 by 1.9 minus 0.5 divided by 1.9 square, and tell me what comes. This will be in radian per second, right? SI unit. Yeah, I will also do.
So just a second. You have taken value of torque as 1. Won't that be 2? Like 0.5 into 2 divided by 1.9 square.
Oh, T is given as what? Oh, 2. Sorry. Yeah, T is given as 2. Sorry. Yeah, good.
Yes, sir.
T is given as 2. Okay. Now what is the answer? So
Coming as 126.037.
126.07. Okay, let me check. So the first term is 126.315. Okay, so this is 126.315 minus.
And that 0.2776.
Okay, let me check. 1.9. Yeah, so this is 0.277. So what is the total you said is
126.057.
57. Okay, now this is in radian per second, right? This is in radian per second.
Yes, radian
So
per
how
second.
do you convert radian per second to RPM?
It's actually omega times 2 pi by 60. I use this assumption. This is actually one of my doubt.
Yeah. So see, for this is very simple. Okay. So how do you, so 1 radian, that you don't think. Okay, you think 1 revolution. Okay. 1 revolution means 2 pi radians, right? One
Mhm.
revolution is 2 pi. Now we have asked that how much is, how many revolutions per minute. So 1 revolution per second will be 2 pi radian per second, right? Correct.
Yes.
1 revolution per minute will be 2 pi revolution per 60 seconds.
Yes.
Yeah. So it will be 2 pi radian per second, right? 1 revolution per minute, that is 1 RPM, is 2 pi by 60 radian per second. Correct? So what will happen is, we want to convert how much? 226, so sorry, what was 126.057, right?
Yes, sir.
Radian per second. This is how much RPM? This is the question. And we know that 1 RPM is 2 pi by 60 radian per second. So what should we do? So
We'll
1
just
by,
reverse that. It will be
just one, it will be
126.5.
1 by x by 2 pi by
Yeah.
60 divided by 126.057, right?
Yes.
So your x will be what? X will be, okay, 126.057 divided by 2 pi multiplied by 60, right? So this is the answer. If you do this, then hopefully you will get this. Let's see, let's verify. Can you tell me whether I am right or wrong? So 2 pi is approximately is equal to 6 only, right? 2 pi is approximately 6, so 6 get cancelled. Let's say this is 10, and so you will get 1260.57, but we did some approximate thing over here. That is why it is 1203.57. Okay, you can, if that quick calculation, okay, but if you do this, I think you should be able to get 1203.574, right? So is your
Yes,
doubt
sir.
clear?
That answer comes.
Yeah. So hopefully your doubt is solved. So whenever you are in confusion, you do this, or what you just remember is 1 revolution means 2 pi radian. That's it. After that you can understand 2 pi radian or 360 degree. Okay. So after that you do by second or by 60, whatever you want. So this is the fundamental thing. After that you can come out of the confusion. Okay, if you are in practice, you do this, then you don't have to do, you directly know 2 pi by 60 or 60 by 2 pi you have to do. But when you are not in practice, even after 10 years you are doing this, you just go to 1 revolution is equal to 2 radians, 2 pi radians. Okay, so let's go to the next question. uh, the only important thing is you don't forget to convert to radians, RPM, before substituting the value over here. Otherwise, you will lose the entire mark. Okay. Operation beyond the rated speed is not possible in PM-DC motor. Okay. I have already explained. In PM-DC motor, the permanent magnets are there, so you cannot change the strength of the magnetic field. Okay. When you don't change the strength of the magnetic field, what happens is, as you have seen in one of the formulas above, okay, this particular formula, okay, the B affects the omega, okay, B affects the omega, but you cannot control B, okay, so you cannot change the omega beyond a certain limit, okay, so that is the reason in permanent DC magnet DC motor you cannot uh, you know increase the speed of the motor. So what usually is done is you reduce the reduce the magnetic field value, so that your speed increases. Okay, that is what is done in wounded type motor where the stator is wounded. Okay, but in permanent magnet motor that is not possible. And the reason is what, the field in the machine cannot be controlled in the PMDC motor, right? So that is the answer. Okay, now let's go back to the numerical part. Okay, so this was the formula we used. Now the motor in question 11 needs to be operated at reduced speed of 800 rpm. Okay, driving the same load by connecting an external resistance in the armature circuit. Okay, so now the value of R is changed while energized from the same DC supply. So voltage is same, right? The input voltage is same, 10 volt, right? Determine the power dissipated in the externally connected resistance. So what is going to change? Can anyone tell me? The load is same, right?
The value of omega must change because there's a different RPM.
No, yeah, but they have given us the value of omega, so we are not worried about that. True. Okay, but they have given us the value of omega.
Sir, external resistance change value.
External resistance, they have said that they are connecting an external resistance. Okay, but how much, what is the value of the external resistance they have given us? Okay, they have not given us. Okay, that we may have to find out. Okay, so determine the power dissipated. Okay, so the because the resistance is changing, the current has to change, right? Or the current doesn't have to change.
If there's a change in resistance, the current will also change because current is related with resistance. I mean,
Okay,
it's a product.
so here can you tell me whether the load is changing?
No, sir, load is same.
Okay, the load is same and the K value is also same, right? The
Yes.
So if the load is same and the K value is the same, whether the current will change, because T into T by K is the current, right?
Yeah. That
Yes,
equation, the
sir.
current does not change if the load and the K constant is same.
Yeah, so the current is not changing. Okay, then what is changing? Or nothing is changing. Okay, so the thing is the power loss, the power that is generated, okay, that is changing. Okay, and the RPM is changing. So these two things are changing. Okay, uh, so let us try to find out this by uh, finding out first what resistance they have connected. Okay, because that we do not know. So let's find out. In this equation we know everything except the RA. Okay, because they have asked us how much power is dissipated, right? So we have to find out what is the total resistance, because then we can say that power is I square R. Okay, so this is our ultimate aim, to see how much the power is getting lost. Okay, so what is RA? Anyone? So this is like too much calculation that we have to do. Let's have some more space.
We'll assume that to be 0.5 only because the resistance is not changing
So
as per
R
the
is
previous.
R is 0.5. We do not know RA na. So they said they put external resistance. Sorry, RA is 0.5. We do not know what is R, right?
Yes, yes.
Yeah, yeah. Okay. So we have been given omega is 800 rpm, and when you convert that 800 rpm to radian per second, you will get 83.7758 radian per second. Okay, uh, for your practice, just do it fast, quickly. 800 rpm, how we will convert? Okay, here I will give you a trick. This is not a right way to do this, but okay, do you remember how we used to convert degrees to radians? Let's say 75 degrees is there, you have to convert to radians. How you will convert?
Pi by 180.
Pi by 180, right? So we knew that when when we have to go from degree to radian, pi should be in the numerator, right? And when we want to go from radian to let's say 1 radian to degrees, what we will do, 180 by pi. The pi will be
Inverse,
in,
right?
yeah. So here also same logic. We have RPM, right? Now we want what, radian per second. So pi should be in the numerator or denominator. We have RPM.
Denominator.
No, we have RPM. We want radian per second.
Sir,
Okay.
numerator.
Numerator.
So 2 pi by 60. Simple. If we have radian per second, okay. Now we want RPM. So pi should be in the denominator, right? Because we want to get rid of radian, right? So just remember this, okay? That will solve all your issues. Okay, simple life. So just remember, when we used to convert to radian, we multiply by pi by 180. That's it. The same analogy over here. That 60 comes because it's per minute. Okay, otherwise that 60 won't come. Okay, so 2 pi by 60 is going to come. The only thing you have to figure out whether the pi is in the numerator or the pi is in the denominator. So if you want to get rid of radian, you divide it by pi. If you want radian, then you multiply by pi. Okay, simple. Okay,
Got it, sir.
yeah. So not recommended way, but okay, that works. If it works for you, then it's fine. Okay, so 83.7758 is there, is equal to voltage we had, okay, 10 I guess, and K was 1.9 from my memory, minus R we do not know, plus 0.5 was given, okay, into T2 and 1.9 square. If you do this, you will get the value of R as 76.2846 ohms. Okay, so for now you can trust me on this, or you can do a very quick calculation, and then we can find the armature current as I is equal to T by K. Okay, so we know 1.9 and this is 2, so I will be what, 1.0526 ampere. Okay, so this current has not changed, but the R value we have got, right? So what is the power loss? I square R. Okay, so this is the power loss, so it will come out to be 1.05 blah 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 square into 76.2 something. Okay, and this value comes out to be 84.526. Okay, let me just make some space. Watt. Okay, fine.
Got it, sir.
Yeah, so
Yes, sir.
yeah. So let's move on to the next question. Okay, so I think this is the last question for today. Okay, in order to avoid the power loss, see, we added the resistance for what, to reduce the speed, okay, to 800 rpm. But what happened, we got power loss, so that is not a good method. So instead what we want to do is, we want to control the armature voltage. Okay, we want to control V. So determine the percentage reduction in the average armature voltage. Okay, or how much you are going to change the voltage, what new voltage you should apply, so that you get a 800 rpm. Okay, without changing the torque. Okay, so he is saying that okay, you get the same torque, but now uh, you change the speed. So you can directly apply this equation. Okay, so you have omega is equal to 80. So what we got, 83.7758. Okay, and we we have to find out what it should be. 1.9 is the K, minus zero point 0.5 is the armature resistance. There is no external resistance added. T was 2 because they said that the torque should not change, right? And 1.9 square. Okay, so now what is the value of V that you are getting? You tell me.
So here we won't consider the external resistance, sir.
So they have said, na, in order to avoid the power loss. So earlier we added external resistance, right?
Okay.
But then what happened? We got power loss, I square R. So he says
So
that
here, yeah, so here they're saying the operating condition in question 13. So
yeah,
operating condition means the original scenario in which the
yeah,
armature was operating.
yes,
Okay.
yes. So he said we don't want to follow that thing of adding the resistance. Instead, we directly want to change the voltage. Okay. So what should be the new voltage? So are you getting 159.7 volt? Actually, it makes sense. See, I think this is answer is right because okay, this is what 0.5 into 2. Okay, see, this is how if you get objectives, then you can do such calculation. 0.5 into 2 is like 1 is 1. This is 1 upon 2 square, that is this will be around 2 square is what, 1 by 4. So this will be 0.25. Okay, minus V upon 1.9. Let's say 2. 1.9 is 2, and let's say this is 80. Okay, we can neglect this very small number. So V will be around 160 volt, around, right? Approximately. So the answer seems possible.
Yeah,
Correct? Yes.
159.70, sir. That's what
Yeah,
I.
yeah, yeah. So that is the right answer, and we have also verified it quickly. Okay, so we have finished all the questions today. Anything else you want to discuss? Please let me know.
Add one question, sir,
Yeah.
just to conclude.
Hmm.
So let's imagine if we are.
Hmm. Your voice broke. Hello.
Okay.
Yeah.
Yeah, yeah. I was actually holding down the space bar.
Hmm.
So if we are given, sir, the speed of the rotor
Hmm.
and we are given 2 different amperes for current draw, that the peak to peak ripple is 1 ampere, but the average current draw is 10 ampere.
Okay.
So how should our approach be? Will we use this W omega formula or will we use the torque formula?
No, no, but what are you asked to find? What do you want to find?
We are asked to determine the average input voltage applied across the armature terminals.
Yeah, so if you are asked to find the average input voltage, so use the
Mhm.
average value, na?
Average value for using which formula, sir? We'll use the omega formula that is right now showing in the screen share.
So you are asked, okay, can you repeat the question?
Can I just share my screen, sir? If it's not
So
inconvenient.
if it is current assignment, no, then I cannot help you. Okay. If you
Okay.
are directly showing me the question from the current assignment, then you should be applying your own experience based on the questions we have discussed from the old assignment. Okay,
Okay.
but I can tell you that by sure that if by combination of these formulas only you will get. You just see
Okay.
what are the given variables and what you want, and which equation has all these variables.
I've
Okay.
actually pinged it in the chat. Basically, it is saying 500 RPM. So my assumption, just I wanted to know the approach. Would I
Okay.
use this omega to do this, or shall I use the torque to do this? I'm not showing anything. I'm just asking that how should I approach this problem?
P for yeah, that's why it's not about showing or something. It's like I cannot
Right,
help you with this directly,
right, right.
but what I'm telling you is that okay,
Mm-hmm.
let me just read the question. For a PMDC motor, a peak to peak ripple of 1 ampere in the current results in the torque ripple of 0.25 Newton meter. Okay, the average
Mm-hmm.
current drawn from the supply is 10 ampere. If this motor is operated at a particular speed of 500 rpm, determine the average input and all that stuff. So basically, see, you have been given a lot of variables, okay,
Mm-hmm.
and you have to find out a particular variable, and that variable is let's say what you have to find out.
Voltage, input
Voltage, yes,
voltage.
input. So in this particular equation, voltage is there, right?
Mm-hmm.
Current is not there, okay, but in this particular equation, torque is there, correct?
Mm-hmm.
uh, do you have they given you the resistance?
Yeah, the
They
resistance is
have
zero point
given
0.5
the
ampere.
they
Yeah,
have given the
yeah.
resistance. You do
Mm-hmm.
only thing you don't have is k.
Right.
Yeah, so that is the hint. Okay, so it's about k.
Okay.
Yeah.
Okay. So that will be reverse.
So
Got it.
that is what you have to figure out based on the no one will give you directly the this thing that you have to even in this question we didn't have the resistance value, we have to find out, okay, and then after that we
Mm.
have to do the power formula. So that way it is like that, so you have to figure out which formulas you have to use. So there are, so let
Mm.
me just uh, uh, do you get these slides, access to the slides or no?
Yeah, I think there's a separate drive share folder
Yeah,
after each recording.
you have, right? So then
Yes,
these
yes.
formulas are there on the slide, so I don't have to do it separately. Okay, so
All right.
these formulas are enough for all the questions.
Just
It's
one
just that you have
last.
to figure out
Yeah,
which one to apply. Huh?
understood. So just one last thing. If I have to calculate k, so will I use the exact assumption of the torque formula, that is torque is equal to k times Ia?
Yeah, that is more specific question. So I think that is
Okay.
I have already given you enough hint. That is
Right, right.
more than enough.
Okay, got it, got it.
Mhm.
Thank you so much.
Yeah. So any other anyone else, if you have question or anything, please
No,
ask.
I think everybody has dropped. It's only you and I.
Okay. 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 Fine. So thank you for joining.
Yeah,
We'll meet next Sunday. Okay.
sure. Thank you,
Bye.
sir.
Okay.